Great, let's see, let me make a couple of announcements here. You go down to the pad, and we'll go over some of this stuff. Let's see. Let me quickly go over it, and then a few things we'll discuss. Friday, that's next lecture, we're just going to have a bunch of demonstrations. Yeah. So, and the idea there is, I guess Leo went off and built a bunch of the circuits that you've fiddled with in your homework. And he built the oscillator and stuff, and according to Leo, it all works exactly like we said it would. So, which is, I knew it would anyway. So anyway, Friday we're just going to do that. It's just going to be, but it'll be fun. It'll be kind of a review of everything we've seen. I'll kind of mix it in with talking a little bit about impulse response and step response and frequency response. But we'll have an oscilloscope here and we'll really do it, and we'll listen to it too. So we'll listen to some convolution and things like that. So that's what we're going to do on Friday. So as far as its pedagogical value, could be pretty good because we'll make some comments about impulse and step response and frequency response and the relation and convolution, the relation between all these things. But then also it's your chance to actually see that that all the stuff we've talked about in this class is quite real, and the predictions you make in this class, the little plots you make either by hand or in MATLAB, are in fact exactly what happens when you build the stuff. So that'll be kind of fun. Let's see, then just to also let you know, today is the last day of material, and in fact, these are just applications, so they're not critical, but it just kind of uses all the stuff. Today we're going to do a really fun application, which is phase lock loops, which I'll talk about that later today. That's actually a really fun application. But then next Wednesday is going to be reserved for review, overview, and then anything I can think of that is missing. That we failed to cover. And actually, if people have questions, if you send them in to me, then I can, vague questions or specific ones. You could say like, I don't get the connection between such and such and such and such. We'll talk about it. Let's see, we should also, I should make an announcement that this is your chance. Tonight, actually, Leo's band is playing at the coffee house at 9. So it's your chance to go and like harass him or heckle him or something like that if you want. Or you know what you could do? You could actually go and then ask him some EE102 questions. I think that would be a good idea. What? That'd be good. In between songs or whatever, you could ask him about Laplace transforms. No. So I should didn't use the microphone. So the question was, will Leo be singing? And the answer was absolutely not. No. Okay. All right. And I guess we should also talk about the final. And I forget when it's actually the regularly scheduled time, and it's got some place too. We'll announce it on the web. What do you? I was kind of thinking it might be okay to have it kind of open notes. What do people think about that? And you want to do this kind of like a couple of pages of notes deal, or just open notes kind of thing?
Open notes.
Yeah? What do you think?
Maybe, I don't know. I mean, like,
One page worked pretty well?
If everybody else wants it.
Yeah, okay. Well, I tell you what, people could just let their opinions be known about this. We don't have to make this decision probably for, we probably have a week. So before we actually start really working on this.
Would that change the format of the test that you write?
Oh, well, would it change? Well, I suppose it would. What it would mean probably, if it was open notes, I don't know, we probably couldn't have any that were like quiz style, right, where you just sat down and did it. No, why don't you think about it, and then we could even talk about it Friday if people have a different opinion or something like that, or if you form an opinion. Yeah, I don't know. Maybe we could make it a couple of pages of notes, or I don't know if that was it useful actually making this page of notes last time, or okay. Well, maybe let's think about it. Okay, so that's it for these various announcements and things. Today we're going to do another application. I guess last time we looked at oscillators, and I kind of rushed. I don't know if people got that or not, and I'm perfectly happy to go over that a little bit or not. So if not, we have this other application that I do want to do in some detail. So oscillators, move on, or?
Maybe you could review it quickly.
Want me to review it quickly? I'm going to review it quickly. Okay. So, in fact, we'll look at a specific oscillator. It is this circuit. It's a classical one. It's I don't know, been used for 80 years, something like that. No, not 80 years. Probably pretty close. So here it is. It's an amplifier that then drives. It's an inverting amplifier that drives 3 RC sections. And if you work out what the transfer function is from the voltage here to the voltage here, I should mention last time that this amplifier has 0 output resistance, 0 output impedance, and infinite input impedance. So no current flows in there, and this drives a voltage. I didn't say that last time, and that, of course, would actually change the transfer function here if it weren't the case. So the transfer function from here to here is given by this expression. It is, you can see that the DC gain instantly is 1, which is what it should be. It has a relative degree of 3 because the denominator has degree 3 and the numerator has degree 0. And that means that at high frequencies, the Bode plot of this falls off at 18 decibels per octave or 60 decibels per decade. Okay? Now, in the time domain, what it says is that the impulse response, or the step response, for example, of this thing has 2 derivatives vanishing at t equals 0. And that's another way of saying that for small t, the step response here is very, very small. And each very, by the way, was like, small, very small, small squared, and very, very small, small cubed. Okay? And of course, we talked last time about why that would be. So basically, I think you should have a good feel for this, that if you pop a step in here, that what comes out here is, for a little while, very, very little. I mean, almost nothing. And then it kind of goes up like that and ends up at 1. Right? So it's a kind of a delay. Anyway, so you wrap feedback around this. And the idea is that if you adjust this gain right, this thing will actually oscillate. Now, this is described by a differential equation, simple third-order differential equation. And you just have to adjust the parameter A so that you have a pair of poles which are pure imaginary. That's one way to do it. Now, you can also do this using feedback. And there, the idea is to have the closed-loop transfer function have a pole at plus minus j omega, where omega is whatever the oscillating frequency is. And that means, in fact, that L here, L is going to assume the value -1 at that frequency. That's the idea. Now, we can adjust A. So, in fact, it's good enough for F simply to have a phase of 180 degrees. If F has a phase of 180 degrees, we can choose A to scale it up or down or whatever is necessary to make the magnitude 1, in which case L will be -1. So that's sort of the idea here. Okay, so to use a feedback method to do this, or to use feedback ideas, we look at the Bode plot of F. We look at the phase. And we'll accept any phase that's 180 or whatever is logically equivalent to 180, like plus 180 we'll take minus 180, we'll take 180 plus 360, whatever that is. But if you examine the phase plot, what you'll see is that the only candidate it crosses is here, which is about 2.5 times RC is the frequency. So sorry, 2.5 over RC is the frequency here. So that's that. And at that point, if you move up here, you can find out what the magnitude is. Okay? The magnitude you can see here is about -30 decibels or something like that, meaning that if you put in, it's a very interesting idea, if you put in a sinusoid here at the frequency 2.5 over RC, what does it look like at the other side? Describe it to me. If you put in a sinusoid at frequency 2.5 over RC, what does this output signal look like? You're going to see these things like on Friday, probably. I mean, the real thing on an oscilloscope. So what's it look like over here? Well, I mean, is it the same frequency as that? Forget the amplifier. The amplifier is gone. Just that little network there. It's the same frequency, sure. What's its amplitude? Smaller. How much smaller? Yeah, it's about 30 dB smaller, which is about a factor of 30. So what you'll see is a little sinusoid here. It's the same frequency, a factor of 30 smaller. And what will be the phase? it'll be exactly 180, which is to say this thing will be exactly out of phase with that. Okay? That's actually kind of interesting to think about, right? It says basically if you grab this wire, put in a signal, and put it up and down right at the right frequency, what comes out here is exactly out of phase. So as this one's moving up, the output's moving up, as the input's moving up, the output's moving down. Okay? Now then, if you adjust A to be 29 or 30 or whatever it is that makes up for it, it will actually regenerate itself. And that's sort of the intuitive analysis. Now you can also do a completely analytical analysis. You can just work out what it means to say the phase angle of L is 180 degrees. That means that this thing vanishes. That's the imaginary part of 1 over L. And that, well, this thing cancels, and you take off one of those, you get a square there, and so on. And you get square root 6 over RC, which is, I hope, something like 2.5 or 2.4 or whatever it is over RC. And there you work out that the loop gain of F is 1/29th, so overall it's minus A over 29. If we choose A equals 29, the system oscillates at this frequency. Now, in fact, this thing is described by a third-order differential equation, and that means there's a third pole. It's got to be real, of course. It couldn't be imaginary, or it'd have to have his buddy there, the conjugate, which is impossible because it's third order, right? So the other one's real, and the only question is whether that third pole is positive or negative. It turns out to be negative, meaning that it represents a decaying solution, not a growing one. And that says that the dynamics of this circuit when A is 29 is it's got two types of dynamics. It's got an oscillation term at this frequency 2.5 over, or whatever it is, square root 6 over RC, plus it's got a decaying exponential term corresponding to that third pole, and that's the idea. Okay, so that's the idea. And in fact, feedback, I should mention, feedback plays a role in basically all oscillators. So that's the basic idea. Okay, so now we're going to look at this last example, and this is it's fun because it's a sophisticated example. It's a good excuse to use all the stuff we know, and it's also one that is very widely used in practice. So it's an excuse for me to tell you about some practical stuff. That's the other reason we do it. So, which of course doesn't have anything to do with the class, but it's just kind of, so you can be, it's cultural enrichment, electrical engineering style. Right? So everyone should know about phase lock loops. So a phase lock loop is basically a little circuit that takes a signal which is usually approximately sinusoidal. So it's an approximately sinusoidal signal, like an FM signal. And what it does then is it has a little oscillator for which it can adjust the frequency of that oscillator. And what it will do is it's a feedback circuit that will adjust the frequency of the oscillator you have there to lock exactly with the incoming frequency. That's the idea. And in fact, it not only matches the frequency, it locks down to the phase. Okay? So this is absolutely critical to basically all modern communications, wireless or by wire or cable and stuff like that. It's absolutely everywhere. So it's a simple application of feedback, and it makes basically all communications possible without it. So I don't know if you remember, we looked at a little communication problem where you were transmitting sort of bits, ones and zeros. You have to know where to sample to decide which is a 1 and which is a 0. And that's done by having a phase lock loop lock onto it. Okay? So this is also how all sorts of wireless stuff works. All sophisticated radio receivers use this type of thing, and so on. So here are some examples of applications. One is to synchronize clocks. So if you have two devices talking to each other over a communication link, their clocks are actually pretty accurate. I mean, crystals these days are very accurate. They're accurate certainly to a part in 10 to the 8 or something like that. But in fact, they drift. And if it's not a very high expensive crystal, it could be off by in the 4th digit or something. And so if one guy thinks he's transmitting, say a communication signal at 1.000 megahertz, the other guy thinks he's receiving it at 1.0, but they're off a little bit, you can easily imagine that the things will eventually get messed up, and you'll be reading the wrong bit and all that sort of stuff. So the way that's done is you have a phase lock loop that locks the two clocks together. So that's the way you do that. And that's very useful. It's used, another example is it's used to sync a monitor or a television signal. So you put in, when you send out a video signal or an RGB signal to a monitor, it should, if it says 72 hertz refresh rate, it's probably pretty close to 72. But it could probably vary from 71.8 all the way to 72.1. Probably that's too big a range. But the point is, whatever it is, if the two weren't synchronized, well, you know what happens when it's not synchronized, is the whole thing slips, and you start seeing the bottom of one frame and the top of the other. That's because they've lost sync. And in fact, if they're off in frequency, what happens is it rolls, right? Because one guy they both think it's 72 hertz, but one guy's actually sending you RGB signals at 71.99, and you can even work out how long it takes for the thing to roll. Okay, so a phase lock loop is what's used to synchronize these signals exactly. It's used in FM demodulation, right? So broadcast FM, these signals are all around 100 megahertz, but the way the signal is encoded in an FM, like ordinary FM signal, is encoded by varying the frequency, by varying that RF frequency a small amount. Anyone know how much? They're about 100 megahertz. I mean, 100 megahertz is the carrier frequency. Or, 88, I don't know what's KSJ, whatever it is, 91 point something, that's megahertz. How much do you think it varies the frequency in an audio when they transmit? Anybody want to take a guess? What is it? Yeah, that's actually very close. It's around there. It's around 15, 20 kilohertz. It's 15 kilohertz. It's sort of a maximum one. And then the spacing between channels is 100 kilohertz. Okay? So what that means is when you're listening to an FM station, the RF signal is basically, it's 88.1 megahertz, and then plus minus, and then there's a few zeros, and then all the signal is in the whatever it is, the fourth and fifth digit of that frequency. So what you are listening to is very, very small variations in frequency of a signal, which is around 100 megahertz. Okay, and the way that's decoded is using a phase lock loop. In an FM receiver, you have a little phase lock loop that locks onto that frequency, and you look at the voltage that's telling the oscillator what to do to track the incoming frequency, and that's your audio signal. So that's how that works. Okay. I already talked about this. It's used to synchronize data communications, and it's also extremely important in I guess in fancy cell phones and in low Earth orbit satellite stuff, which is just coming online now. These things like Iridium and all that sort of stuff. Those work by having these satellites which are in low Earth orbit, so they're moving very fast around the Earth, right? So it turns out when you turn on one of these things, the satellite is transmitting at 1.622 gigahertz. You remember from your physics class that this thing is moving at it's not a huge fraction of the speed of light, but it's big enough that that the frequency you receive is substantially different from the frequency being transmitted. Okay, simply because it's coming at you and they're moving fast, right? So what that says, two interesting things. It says if I have an Iridium phone and I make a contact with a satellite, which is supposed to be transmitting at 1.6 gigahertz. I'm actually receiving it now at 1.605. I mean, a very considerable increase in frequency. Okay? What happens is it flies overhead. When it's directly overhead, it is in fact now 1.6 gigahertz, right? And then as it gets in back of you and recedes, it's now lower. So what's happening is, if you think about it, the RF signal I'm locking to varies over this huge range. Right, and if I just fix my receiver at a given frequency, you will hear absolutely nothing, or you'll hear some weird combination of all sorts of people's conversations, depending on which satellites are going which way, and this kind of thing. Well, basically, no, it just wouldn't work. So these are just some applications of what you use phase lock loops for. And in fact, these are interesting problems because it means when you fire up one of these telephones, it doesn't even know what frequency to listen for. Right? It has to actually start scanning. It has to scan over frequencies. Then it figures out where it is. Once it knows where it is, then it knows all sorts of other stuff. Anyway, so it's complicated. Okay. That's on where phase lock loops are used. So here's a basic block diagram. Looks like this. There's a phase detector. So there's an incoming signal, which is sinusoid, but it could be a square wave. It doesn't really matter much. Or a pulse train. It doesn't matter too much. But it's got a frequency, omega in. And I really shouldn't say, casually we say this is a sinusoid. The truth is it's not a sinusoid. It looks like this. It would be a sinusoid if omega were constant. This is a sinusoid. So if there are sort of mathematicians or lawyers present, you could not say that this input signal or this signal is a sinusoid, because a sinusoid by definition has a constant frequency. But if there's just, regular people around, you would say it's a sinusoid with varying frequency, right? It would be like saying, what's the signal coming out of an FM transmitter? And pretty much it's a sinusoid at 88.1 megahertz. And then if someone says, really? And you say, well, no, in truth, the frequency varies between, plus minus 15 kilohertz around that, which is in the fourth digit. So anyway, you get the idea. So these two are sinusoids. And we have a little box, I'll explain even how that works, called a phase detector, which checks the relative phase between two sinusoids. Generates a voltage proportional to that phase error, like this. Then this goes through a loop filter. We'll see what that does in a minute. It smooths out the phase error and generates a voltage which goes to a VCO. That's a voltage-controlled oscillator here, which is a little box that has the following property. It's got an input signal, which is a voltage, and the output it's an oscillator, except that this input voltage controls the frequency. Okay? Now, in many applications of phase lock loops, the ranges of frequencies we're talking about are measured in their sub-fractions of a %. Okay? So in other words, if you were to just casually examine this circuit, this would look like an oscillator. You couldn't look on an oscilloscope and see that the frequency was varying. That you couldn't see it. Although there are PLLs which have a wide lock range, but normally, the frequency here varies only just a little tiny bit, like that. So this varies, and it's modulated by this voltage here. And there's lots of ways to make VCOs. So for example, using the RC one is a very common way to make a VCO. And the capacitors are actually active devices, and by changing the bias voltage, you change the capacitance, and that sweeps the frequency. So that's one way to make a VCO, but there's lots. Okay, so this is the idea, and the idea here is, if you build this right, is you have feedback. And what happens is, if these two guys here are transmitting, if they're phase locked, in other words, if the frequencies are equal, the phase is some constant number here, and this voltage is constant, and this thing is matched to that. If this frequency increases, what happens is rapidly the phase error starts increasing. Here. What that does is it instructs the VCO to start increasing its frequency to maintain the lock. And that's sort of the intuitive picture. But basically, it's a feedback system. It's not a simple one because some of these signals are really sinusoids, and some are voltages over here. So that's the idea. Or actually, in a lot of real circuits, these are currents. Well, this signal, for example, is a current. But this is not relevant. Okay. So let me show you what I'll describe what the phase detector does. That's the first part of this circuit. The phase detector looks like this. It puts out a voltage which is proportional to the phase difference between these two input signals. And in fact, I don't know why these are in this order. It might have had something to do with the fact that I was writing these 15 minutes before class, but I can actually show you. I'll show you how a phase detector is built. What it does is it generates a voltage which is proportional to the difference in phase between these two signals, and the difference in phase between the two signals is the integral of the frequency difference. Okay, and phase detectors usually work like this. They generate a voltage proportional to the phase error. Except, of course, it can't work that. Phases, of course, as you shift over a circle, well, you know what, 360 is the same as 0. So you could hardly have a linear phase detector that works everywhere. So it's going to fail somewhere. And they typically fail over a range like plus minus 90 degrees or 0 to 180 or something like that. And that's the idea. And if you see a phase detector, it'll be given in terms of a detector gain, which is in volts per. Yeah, that's right, volts per radian, which is a phase. It's just volts. So let me show you quickly what one looks like, and then you'll get the picture here. So here's a kind of a common phase detector. It works like this. One signal comes in, and here's the other. The first thing you do is you send it through what people call a hard limiter or a sign detector or whatever. We discussed this early on. And what that does is that turns this signal, if this signal is a sinusoid, it turns this one into the associated square wave, which just gives you plus or minus 1 depending on the sign of that. This one here is also turned into a square wave, like this. That's that. Then we multiply these two, but of course multiplying plus minus 1 signals is really just it's an exclusive OR. So this is actually digital logic. It's not, I mean we show it as a multiply here, but it's in fact it's nothing but an exclusive OR, right? It's digital logic. Then that signal goes through a filter here. So here's a picture showing it. Here are two signals, and you can see they're not locked. There is in fact a phase difference. It's this. And what happens now is you multiply the two together. You get a new signal, which is 1 for all of the time when they're both positive, right? And then it's minus 1 otherwise. And now if you think about this, if these two signals were deadlocked in phase, 0 phase difference, what would this signal look like, the product? If they were deadlocked, if they were perfectly locked, what would the product of these two square waves look like? What? It'd be constant. It would just be the number 1, right? What if they were absolutely anti-phase, so they were locked at 180 degrees apart from each other? If they're 180 degrees phase shift, what do these things look like then? What is the average value? Or what does the signal look like? It's just minus 1. Because what happens is this guy's 1, this one's minus 1, and then at the very same time they switch, and one becomes 1, the other becomes minus 1, and the product is always minus 1. Okay? What if they are 90 degrees out of phase? What happens then? If they're 90 degrees out of phase, what does this signal look like? The product. Want me to draw it? I'll draw it. Here. 90 degrees out of phase would look like this. Here's the other signal. So if you take the product of these two signals, what do you get? Yeah, you know what you get is you get a perfectly regular square wave at twice the frequency. Okay? And what is the average value of this thing? What's the average value of this thing? It's 0. Okay? So what we've already seen is pretty obvious, right? That when you take the product of two square waves at the same frequency, and then you look at the average value of that signal. I mean, at one extreme they're locked. They have 0 phase difference, and you get the average value is 1. At the other extreme, they're 180 degrees out of phase. You get minus 1, and right in the middle is 90 degrees, and you get a signal which is a square wave, but its average value is 0. And so the basic idea there is that the average value, if you look at the average value of the product as a function of the phase difference, it looks like this. You can just work it out. So this is not exactly a linear relationship, but if you look over here, for example, it is. So this phase detector, this works as a phase detector from 0 to 180 degrees. As a linear phase detector, that is. Okay? So that's the basic idea. Okay, so that's the idea behind how you build a phase detector. They kind of look like that. I mean, this is actually not a bad picture of what a phase detector looks like. Looks something like that. Okay, so that's a phase detector. That's how they work. And what it does is it takes two signals in, and it generates a voltage here, which tells you the phase difference between the two signals. So that's the idea. Okay, that's the phase detector. The voltage-controlled oscillator, that's another component in this thing. That's down here. And that works this way. It's a little box that generates a frequency-dependent sinusoid with its frequency depending on the input voltage. So in other words, the oscillation frequency is given by a constant, which is traditionally called the free-running frequency. It's the frequency of the oscillator if the control voltage, that's what this thing is called, the input to a VCO is called the control voltage. If that's 0, then the oscillator is said to be it's in the free-running. This is the free-running frequency. And then it's proportional to the voltage here. It will actually bend the frequency. Okay? So in real VCOs, they'll have a minimum maximum frequency. Like for example, this VCO is meant to it's meant to operate between 1.23 gigahertz plus minus, and then it could even be something very small like 100 megahertz. That doesn't sound small, but well, plus minus 50 megahertz or something like that. Or for example, to receive an FM station, something like that, the range of the VCO here would probably be only about plus minus 20 kilohertz. That's all. Okay, so that's how that works. Okay, so that's a VCO. So let's go back to the picture here, and now let me show you how we can actually analyze this. It's obviously a very complicated thing here, right? This thing's highly nonlinear. Real VCOs are quite nonlinear. But in fact, there's a perfectly reasonable model that we can come up with that will certainly tell you the basic ideas of how a PLL works. So here it is. I made a block diagram out of this real system, and it looks like this. I have my incoming frequency, omega in. I subtract omega os from it. That's the oscillator frequency. This is the difference, and I integrate it to get the phase error. And that part of the block diagram, it doesn't exist as any real part, right? There's no physical part. It corresponds simply to this fact here, that the phase detector gives you something proportional to the phase, which is the integral of the frequency. So this does not exist in physical form. But for us, this is it. This says that theta is, I guess I have here, sorry, that's theta error, and then you multiply by k det, that's V phase. So this is the voltage here generated by the phase detector is proportional to the difference in phase. Then we go through G of S, that's the loop filter, and this goes into our oscillator. This gives us our frequency change, and we add that to our base frequency, which is omega free run, because if I turn that off, I get an oscillation frequency of free. That's my oscillation frequency. So that's it. Now what's neat about this is we can understand this. This works. This is 102 stuff right here, right? Because it's a system with I don't know, transfer function, integrator, block diagram. This is what we've been doing. We can do this. A couple of input signals, stuff like that. We can handle this. Now, this model, by the way, is good provided we don't violate a few things. For example, this oscillation frequency obviously has to stay within the range that your VCO can handle. If it goes out, if it exceeds that range, then of course the linear model is no longer good. The one that really is often the thing that kills you is this phase error here. That this linear model is valid only provided this phase error stays in some range. And a typical VCO could be 90 degrees, but more often it would be 70 or 60 degrees. So it would swing plus minus 60 degrees. Beyond that, all bets are off. Okay, so this is, I guess, like the normal situation. Every time you draw a block diagram, there's always a caveat below that says that this model is accurate provided certain things happen, right? So, which is true, of course, for when you write down, like you look at an op amp or something like that, and it's accurate provided, for example, the input voltage is less than plus minus something or other, and so on. So same here. Okay. Well, let's analyze how this works, and let's figure out what we're interested in. Here are the things we're interested in. Let's look at some transfer functions here. Here's one. We'll be very interested to find. I'd like to know what is omega. What's the oscillation frequency in terms of omega in? That'll be really interesting. For example, what's the DC gain of that? It would tell you what does omega os settle out to when omega in is constant. Hopefully, I hope the answer is omega in, right? That's the whole idea, is that this system, if we do it right, is supposed to settle out so that this is equal to that. Already, though, you see some really good signs here. You see a feedback loop, and you see an integrator. So just as a crude, intuitive idea, you should say, oh, this is very good because this is integral action. We have to analyze it all, right? But you should say that's integral action, and that means if it's stable and if we can make it work and all that, it says that in fact this error is gonna go to 0. That's exactly, look, that's just what we want. We want omega in minus omega oscillator to equal 0. So hopefully it's gonna work. We'll see that it does. Okay, so that's the model. First we'll calculate the transfer function from omega free to omega os. So you calculate the transfer function from here to here. That's something you can do very easily, which I won't subject you to. I did it. And the transfer function from omega free to omega os is this transfer function here. It's s over s plus k det k os times g of s. Okay? Assuming that this thing is Hurwitz, in other words, its poles have negative real part, if I plug in s equals 0, this thing vanishes. And that's really interesting. It says that this omega free in this model has no effect whatsoever on the oscillation frequency, which is kind of weird. That's kind of like integral, it's like integral action. And what that basically says is that no matter what the free running frequency is, this thing will tune this oscillator to lock to this thing. Okay? So at least in this analysis, omega free goes away. It's going to come back soon. Okay, now let's look at the transfer function from omega in to omega os. It'll be very interesting. Its DC gain is going to have a very important meaning. The step response will be interesting. What would the step response mean? What does step response from omega in to omega os mean? Physically in terms of a PLL. What does it tell you? How would you see it? What would it look like on an oscilloscope, for example? What does it mean? Would you, I don't know, suppose I told you that the step response looks like this. What does that mean? Yeah, what it means is, it means that if this input frequency was at 88 megahertz or 1.2 gigahertz and rapidly jumped to another frequency. Now, we're not talking radical jumps in frequency. We're talking about, 0.1%. If it rapidly jumped in frequency, the question is, this shows you what the frequency of this is. And it would tell you that it takes, whatever this is, 1 millisecond or, I don't know, whatever it is, 1 nanosecond or something like that, before this frequency tracks that one. And when it's up here, that means it's tracking again. Okay, so that's what that means. That's what the step response means. It tells you how fast this thing can react to a rapid step in frequency and readjust its own oscillator to, again, phase lock. That's what it depends on. Okay. The question?
What's omega free again?
It's not a, no. This is the VCO right here, and it's not a disturbance. It's actually just part of our oscillator. Right now, it looks silly. Well, for one thing, it doesn't do anything yet, but we're going to see actually soon that it actually does play a role. Right. Okay. So this is if we work out this transfer function from here to here, it turns out to be precisely this. It's k det chaos g of s over s plus k det chaos g of s. That's it. So now we have a complete analysis. If you pick a stupid g of s, this thing might even be unstable. That means you'd have a completely useless phase lock loop. If you pick a good GSS, this thing might be stable, and this transfer function will tell you all about how rapidly this thing will adjust to input changes in frequencies. How rapidly will it track it, and all that kind of stuff. Now the really interesting part is this. If you plug in s equals 0 here, you will get simply 1. That's great. That's just what we wanted. It says that if this frequency is constant, this thing will adjust omega os to exactly match omega in, period. That's what it means for the transfer function from here to here to be 1. I mean the DC gain to be 1. It will lock it. Okay? And that's what we wanted. Of course, that requires this thing to be stable and so on. So let's look at a couple of examples here. The simplest PLL is called a first order loop, and they just take G of S equals 1. So this box isn't even here. It's just not even here. Notice the phase error just gets fed directly into the VCO. And if you do that, you end up with a transfer function from omega in to omega os of 1 over 1 plus S over K det chaos. And this is why it's called a first order loop. And in fact, what you see is that it's a first order system. It's got a bandwidth which is set by K des is equal to K des chaos. And it says, for example, that the step response looks just like it did in 101. It's just that. Okay? So that says if two communication systems are communicating and something happens to the oscillator, like somebody bangs the desk over here and the crystal has some weird dislocation, and the frequency changes rapidly by a small amount, then the frequency at the other end, so if this is the frequency of the transmitter, like that, then the frequency of the receiver will look like that. Okay, so that's what it looks like. This time will tell you how long it takes to lock, the frequency, to reestablish lock. Okay, so that's the idea. If you have a second order loop, this is actually, first order loop isn't used that often. Second order loop is widely used in practice. And here you take G of S to be first order, and when you work out this transfer function from omega in to omega os, it's second order like that. And there are several things people do, and in fact, when you get a little application manual or something like that, they'll even give you various choices. And depending on the application, you might pick the poles. One common one is to pick them double like that. Another common one is actually to pick them like this. Right? What you have to remember is when you pick these poles to have equal real and imaginary part, although the response is oscillatory, it decays so fast that you only see like 1 or 2 bumps. So, and depending on the application field, it's traditional. Depending on the application, you might do this or this. And in fact, other people do that. There's even reasons to split the poles and all that kind of stuff. This is the idea. You split the poles, and what you end up with is that omega os is the second order low pass filtered version of omega in. That's the way that works. Now the last thing we can do, which also uses just purely material from the course, is to analyze the lock range. And usually it's not the oscillator that limits this model. What limits the model is that phase error. That's what limits it. Okay? If this phase error gets more than 90 degrees, for example, then this model is completely wrong. For one thing, I'm drawing this as a linear phase detector, but the truth is this thing is a complicated nonlinear function that looks like that. We saw it, right? That's the voltage out as a function of the phase. Well, if I actually put this model in here, the dynamics is incredibly complicated, right? So what we'll do is we'll simply say, let's see what well, you can even imagine what happens. If the phase slips over to here, it's equivalent to the sign reversing. The dynamics then becomes actually unstable. And so it actually flips over to the next cycle, and it's all very what happens in it is very complicated. So we'll look at what's required to keep this thing less than 90 degrees. And there's lots of interesting things to do. For example, we can work out the DC gain from omega in to theta air. Very interesting number. Okay? Because that'll tell you the lock range if omega in were very slowly varying, right? If I vary this thing too much, this thing gets out of its 90-degree band, and this model is completely wrong, and the whole thing goes nuts. In fact, it goes into wild oscillations and stuff, which in fact is what you hear when you hear sort of static on FM between stations. Although these days they mute it so you can't hear it. But if you unmute it, that's exactly what you'll hear. You will hear the sound of a phase lock loop losing track. And it just sounds like noise. It just goes nuts. Very, very, very complicated. Okay, so what we'll do is we'll calculate the transfer function. Turns out we'll calculate the transfer function from omega in minus omega os. That's this signal here to theta error. And when you do that, you get this transfer function here. And you can now, for example, plug in omega in constant. I mean, sorry, if it's constant, you plug in S equals 0, and this is your theta error. This is your phase angle error. The rule is now that this error must be less than pi over 2 times, well, this thing here has to be less than absolute value, say 90 degrees or so, something like that. And that's the same as this. If you multiply this, put that over there, you get this expression here. So that's the lock range. That's the lock range. And now you see omega free is actually rather important because the lock range is symmetric about omega free, which makes a lot of sense. Is there a question?
Professor Boyd, how are you calculating the transfer functions? Are you doing
Here?
it directly from the diagram?
Yeah. You mean how do I do it personally? A lot of these things I can guess and write it down, and just look at it and figure it out. But often I'm wrong. So I do it the way you do it, which is I sit down in a quiet place and I write out all the equations and I eliminate a bunch of things and I express this, the Laplace transform of this, as a linear function of the Laplace transform of that minus the Laplace transform of that. So that's how I do it. I'm sparing you that. But no, I mean, so in fact, I do it the way you do it, same way you do it. That's actually something I should probably mention. I guess some people have said that it's when we study feedback, it's complicated because we have these two different block diagrams. And it's worse. Anyway, my comment on that is, welcome to real life feedback. Real life feedback doesn't fit a fixed format. I mean, some things are common, but I mean, here's a real life feedback system, and it's got 3 boxes here and 1 below, and 2 inputs. So, and I wish I could tell you that there was some cool rule about how to adapt a given real feedback system to one of our formulas, but I'm sorry to report that there isn't. That the best way to do is just sit down, write out all the equations, and some things will be common. Like, for example, the loop gain for sure is this times this times this times that, right? But you'd have to write it all out. And in fact, people can do sneaky things. Like there might be a minus sign here, in which case the loop gain would be the negative of that. And so your best bet is just analyze the block diagram as if you've never heard of feedback before. I wish there was a clean way, or I wish people who use feedback would standardize on a certain block diagram, but it hasn't happened. It even varies across companies. So for example, companies that widely use feedback will actually fix a feedback structure and then refer to it internally as if everyone knows what it is. And it'll be different. And they'll do sick things, like sometimes they'll have a plus here and sometimes a minus. That depends on the company. Then, of course, when a new employee comes from another company and they get the sign wrong, well, you can imagine what that does to like an altitude hold system on an airplane. Anyway, we already discussed what happens when you change the sign. Okay, so that was a long answer to how did I get this transfer function. But I got it the way you got it. I write out all the equations in a quiet place, and I do it 2 or 3 times, and I wait until I get the same answer. Let's say for 2 out of 3, let's say. And then I declare that to be the transfer function, which is, I think, probably what you do, right? Is that how you, that's how you guys do it, right? Yeah, okay, so same thing. Okay, so anyway, this gives us our lock range, and I don't know, we probably won't do this on Friday, but I have done this before, and it's pretty amazing. This is pretty close to the way it really works. So if you take your input frequency and you turn the knob, it'll track perfectly until you get up to a number around this, except this might not be 90 degrees, but 70 or something. Then the thing starts going nuts. The first thing it starts losing lock and stuff like that, and then eventually it just goes wild. So that's the lock range. And we can repeat the lock range analysis to tie in something else from our course for rapidly varying omega n. And that turns out is an exercise in peak gain, because you have a convolution system, and you have an input which is limited in magnitude, and you want to know what's its effect. How big a signal can it make somewhere else? Specifically, how big can it make theta error? Because if it makes theta error as big as 90, it's not going to lock, or you can drive it out of lock. So that's a peak gain calculation, and I've done some of it, and you work it out. I didn't work it out for the second order case, but for the first order case, you find the lock range is the same as that predicted by the DC gain, and so on. All right, let me finish. So what this is this is sort of the 102 version of phase lock loop, and an amazing fact about it is that even the most sophisticated analyses are not much more complicated than this. I mean, this basically tells you most of what you need to know about phase-locked loops. Because it turns out that if you actually take into account the fact that the phase detector looks like that and is not just linear like that, it turns out, as you, I'm sure, would guess, that you have a fantastically complicated nonlinear system. So in that case, the real analysis of losing and acquiring lock is very difficult, totally incomplete. So maybe one of you will work out a real theory of acquiring or losing lock. On the other hand, there's probably around 1 billion working systems that use phase lock loops. So there's a lot known in practice about how they track, how they lose lock, and all that kind of stuff. So it's kind of interesting. But you get a very, very good idea from a 102 based analysis. So, okay, so we'll quit here, and then on Friday I guess we'll do these demos and stuff.